find our poll everywhere, go ahead and get logged into that. It's going to be sort of our usual process. And here are our lesson objectives for today. So after this lesson, students will be able to name the parameter that controls T1. We did talk about that a little bit last week, but we're going to get into a deeper explanation of what that is this week. We're going to be able to explain what TR is and how it works. You'll be able to name the parameter that controls T2 weighting. And again, we mentioned it last week briefly, but this week we're going to, again, delve deeper into exactly what that means. You'll be able to explain what TE is and how it works. You'll be able to describe proton density weighting and how the TR and the TE affect it. There was a question from the homework about the heat analogy, and I'll try to explain that a little bit better. You'll be able to describe the events in a basic spin echo sequence. So we're now going to start introducing the concept of what is a sequence, what does that actually mean? And then finally, you'll be able to identify the relative lengths of those different parameters in order to obtain the three different main types of weighting, the T1, the T2, and the proton density weighted sequences. So let's delve right in here. So our T1 weighted image, as we talked about last week, is controlled by the parameter called TR. And the reason for that, and we can see it here on the graph, is that that short TR is going to maximize those T1 differences. So recall what T1 relaxation is we start here at equilibrium, we flip 90 degrees, right? And then we start to recover back down to equilibrium. That's our T1 relaxation that our protons do. And so what we want to do is we want to maximize the differences in our tissues based on their T1 time, so that we have sort of this situation where there's a big difference between them, where we don't want to wait too long, because now they're going to all relax back and they're not going to have enough difference in their T1 contrast. So that short TR is going to maximize those T1 differences. If we were to use a long TR here, and you can see that in the blue, that minimizes the T1 differences. And so when we talk about making a T1 weighted sequence, we want to maximize those T1 differences. Okay, but what is TR? TR stands for repetition time. Don't ask me why they don't call it RT, it's TR, but that's what they call it. But it is the time between when we excite one slice to 90 degrees to when we come back and excite the same slice again. Okay, so we're getting into talking about we're selectively going to excite our slices one slice at a time, okay? And so that TR, that repetition time, is the time between slice one's excitation, and then we do all of our other slices, and then we come back and we excite slice one again. That's length of time is what is known as TR, or repetition time. During that time, all of the other slices are selectively excited. So we start at slice one. If you got 25 slices, you're going to go 1 to 25, and then you're going to come back to 1, okay? But the really key thing here is that while all the other slices are excited, the first slice that got excited is going to experience that T1 relaxation, right? Because we've excited it, then we turned off our RF and we collected our signal, and then we moved on to all of our other slices. Well, slice one's just sitting there hanging out now, right? And it's experiencing that T1 relaxation. So let's look at a picture of kind of what this looks like. So here we have our 90-degree pulse for slice number 1 here in red. And then we've got our 180 pulse, which we'll talk about in a little bit. And then we have our echo. Our echo is basically our signal. Okay, so when we talk about spin echo, echo just means signal. Okay, that's what the signal that we are collecting. So here we've done slice 1. And now we're going to move on. We're going to do the same thing for slice 2. We have excitation, we have a 180, we have a signal. Now we move on to slice 3, same thing. Slice 4, same thing. Now we come back to slice 1. This length of time between the red arrows is our repetition time, our TR. And depending on how long we wait between excitation of slice 1 and when we come back to slice 1 is going to determine how much T1 relaxation we allow to happen, all right? And so as we've established, we need that time period to be short, right? Because if we wait too long, our tissues are all going to be relaxed back and there won't be any difference between them. So for a T1 weighted, that's why our TR is the factor that controls our T1 weighting, because it's how long we're waiting before we come back to the slice determines how much T1 difference there is in the tissues. With me so far? Okay. So each slice does require multiple excitations to get enough data for an image. And again, you have to be able to do all of the slices within that TR. So if you've started to notice in clinic, when you're doing a T1 sequence, those TRs are like in the 5 to 700 range on a 1.5 Tesla, right? They're short. Well, that's a short TR. And so we're not allowing very much T1 relaxation to occur so that we have that big difference. One question from the homework, can you simplify spin echo timing parameters? That's kind of what this graph is showing. So we're showing here that we've done slice 1, we do all of our other slices, and then we come back to slice 1 for our repetition number 2. And we're going to do this multiple times in order to get enough data for our image to be recreated. All right? Let's see, what else from the homework? Okay, that was the only one on this one. With me so far? Okay, so let's talk about T1 weighting. So our short TR allows very little T1 relaxation to occur before we come back to that slice, so that when we come back to it, remember, everybody look at me for a second, my crazy arms. So we want, next time we come back, to have a big difference so that when we flip it again, right, the water's the one that's giving us the signal and the fat is not, okay? Or sorry, other way around. Water is, but the fat is giving a signal, the water is not for a T1. So that's why we need that short TR, is so that we have that big difference in our T1 relaxation between our tissues. So we're maximizing those differences. And then remember, we do have to talk about TE, our echo time, which we'll get deeper into, but our short TE allows very little of our T2 relaxation. Remember, T2 is this, when it's out of phase in our transverse plane, right? We lose signal in the transverse plane because they're getting out of phase. And so we want to allow very little of that to happen. We want them to be as in phase as possible. So we're going to use that short TE so that we don't have T2 differences contributing to the weighting of our image. All right, we want one of these types of factors to predominate over the others. Okay, that's what we mean by weighting. And again, as I mentioned last week, the terms short and long are very relative. Okay, so don't compare TE to TR as far as short long. Compare TR to TR. So apples to apples. Okay, when we talk about short and long. And you can see that here in this graph. So here is the combination of our two different factors in a T1 weighted series, is that you have that short T1 because you want these big differences here, right? But you have a short TE because you don't want there to be T2 differences. Okay, so this graph kind of brings that all together, is you want a short short TR so that you have that T1 difference, but also a short TE, so you don't have T2 differences. Does that make sense? Questions on that? All right, let's take a poll. So what does TR stand for? Job, guys. Yep, good job. So yes, our TR stands for repetition time. And again, that's the time between slice 1 excitation, and we do all of our other slices, and we come back to slice 1, and that's our TR. All right? Questions on that? Oh, are we good? Good, thumbs up, love it. Okay. So remember we talked about vectors last week, and we talked about how a vector has both a direction and it has a magnitude. And in order to figure out how much component of each of these axes we have, we just draw our little lines across. So here our red arrow, we have a large amount of y, we have a very small amount of x. It doesn't go over very far, but it goes up very high, okay? And then the opposite here in the yellow, we have a very small amount of y, we have a large amount of x. And again, why this becomes important is because we're not talking about just at 90 degrees, we are talking about maybe different angles, right? These two tissues have different angles. They both have a different component of each of these two axes. And that's what we're looking for, is because the more transverse you have, the higher the signal you're going to get from that particular tissue. All right, so we're looking at the transverse as the signal that we're collecting. So here's how T1 works. We start with everything at V sub 0, right? That's our first thing. We just put our patient in, everything's lined up with V sub 0. Then we flip it 90 degrees, so everything goes from here to here. We'll all agree this is a 90-degree angle, right? This is a right angle, all right? And again, keep in mind, this is not stationary, this is spinning. So it's kind of spinning around this axis now, the transverse axis, all right? This is just meant to sort of show you the process that happens. Then we've established that fat relaxes very quickly back down to V sub 0. Water, not as quickly. So we get this difference between our two tissues. And again, spinning around here, okay? Then we come back to this slice and we excite it again, and look what happens. So we'll agree again, this is a 90-degree angle. You can sort of see the shadow of where it got to, this fat, right? And you can see the shadow of where the water got to. Then we flipped it. And so now, when we look at how much transverse component we have, water has a very small amount because it's all the way down here, right? Whereas our fat is kind of more up here. So it's got a larger transverse component. Therefore, fat is giving us a stronger signal. This is our T1 weighting, right? We have that bright fat and we have the dark water. Yeah, see some nods, that's good. I'm going to go back. I did have a question from the homework. So the question was, a 90-degree pulse flips the protons from parallel to anti-parallel. But this particular question says that when something flips from parallel to anti-parallel, they're thinking that it's 180. It's not. Anti-parallel is anything that's not parallel. So when you say the word anti, just think the word not, okay? It's not a particular, it doesn't have to be 90, it could be 180. 180 is also an anti-parallel position, all right? Anything that's just not parallel is considered anti-parallel, okay? So kind of try to get that sort of fixed notion of, oh, it's got to be 180 out of your head, because it could actually be anything between these two, between 0 and 180, basically. As long as it's not parallel, then that's considered anti-parallel. So I just wanted to address that from the homework. Okay, so we got to this point. So we've got our bright fat, we've got our dark water, because we had a short enough TR that we didn't let them both get all the way back down, right? Now, if our TR is too long, this is what happens, is they both get pretty far back to parallel, right? So that when we flip it again, now they both have signal, right? And so this is why we can't wait too long, because we don't want them to be together. We want them to have separation. And so this is showing you that if we started here and we waited too long to come back and re-excite that slice, now they're both giving us signal. And that's not what we want. We want to have contrast between our tissues, right? If they're too similar, we're not going to have those nice high contrast images. All right? So there's hardly any difference there, which is not what we want. Questions on that? Okay, so let's look at an image. You've all seen these by now, I'm sure. So here we have our TR was 500 and our TE was 20. and you can see this nice, good contrast image. You've got this nice dark water, you've got your brain matter, and you've got your fat around the periphery that's nice and bright, giving us a lot of signal. And so this is our T1 weighting. Questions on T1 weighting? Good at home? Okay. All right, let's take a poll. Which one of these is a T1 weighted image? We're looking for that nice dark water, nice bright fat. There we go. There we go. So yes, the answer is A. So it's the dark water that you're looking for, and that bright fat around the edges, and then your gray matter is kind of in between. All right. So what imaging parameter controls T1 weighting? Great job, guys. Yes. So the TR, the repetition time, is what controls that T1 weighting. Excellent, excellent. Okay. All right. Questions on T1 before we move on to T2? We're good? Okay. T2 weighted imaging. So again, recall that we talked about this last week. The parameter that controls our T2 is our TE, and the reason for it, again, we can see here that our short TE minimizes those T2 differences. So for a T2 weighted, we need that long TE because we want to maximize those T2 differences, maximize how much dephasing has occurred in our tissues. All right, I'll give you a minute if you want to. Of course, you've got the PowerPoint though. Yeah, okay. All right, so short TE minimizes T2, long TE maximizes T2, but we're doing a T2 weighted imaging, so we want to maximize it, which means we need a long TE. But what is TE? TE, and again, it's not ET, it is TE, but it stands for echo time. And echo time is the time from when we excite our slice to when we collect our echo or our signal, okay? So that's for one slice, all right? And so we excite slice 1, we collect our echo, we excite slice 2, we collect our echo, we do that for all slices, right? So each slice has to be excited and an echo collected during each TR. Remember I said we have to be able to fit all of our TR, all of our slices within our TR, all right? But what that means is that we're gonna have multiple TEs within our TR. And while all of our other slices are being excited, again, the first slice is just sitting there, right? Experiencing our T2 relaxation, it dephases, all right? And so in this situation, we want to wait a long time before we come back to slice 1, so there'll be a lot of difference in the amount of dephasing that has occurred, T2 dephasing, right? So let's look at this image again. So same as before, here we did slice 1, excitation, 180, and echo. This distance here, this time here is our echo time. It's the time from when we excited it to when we collected our echo. But notice we have multiple ones of these in our TR, right? We have to excite each slice in our TR. So if we're exciting it, we have to collect an echo, right? Or we're not getting any signal. So we're exciting it, we're collecting our echo, then we move on to slice 2, we excite it, we collect our echo. And so multiple TEs within the larger length of our TR, depending on how long that is. And if you've noticed in clinic at all, has anyone experienced the situation where you had to increase the number of slices and it wouldn't let you, right? It's because you've now exceeded the number of slices you can fit within whatever that TR. Now, typically this happens on T1 because it's short, but this is why. It's because we have to be able to fit that TE for every single slice within the time frame of our TR. And so this is why that happens. Sometimes you have too many slices and now you've exceeded that time limit. One question from the homework, please explain tau time. So tau time is basically the time from when we excite our slice to the time when we apply our 180 rephasing pulse. And so that means, and it's exactly half of our TE, okay? So our TE is always gonna be twice whatever our tau time is, all right? So the time from excitation here to the 180 pulse, that's tau. And then the other question from the homework, does tau time affect contrast? Yes, absolutely, because the tau time basically is going to determine what your TE is, correct? And we now know that TE affects our T2 weighting. And so, yes, it is absolutely related to your contrast there, your weighting that you're trying to achieve. All right, so how does this work for T2 weighting? So we have our long TR. So in this case, we don't want there to be T1 differences, right? We want T2 to be the predominant factor that is affecting our contrast, correct? So we want to minimize how much T2 differences there are, which means we want now to wait a long time, right? We want them to both kind of be at the same place in that relaxation back towards B sub 0. So there's not a big difference between them. What we want to look at is we want to look at the dephasing differences between them in this transverse plane. All right, and remember, again, fat dephases very quickly relative to water. And so if we wait a long enough time, the fat's going to be pretty much dephased, which means pretty much no signal. And our water is still going to be pretty well in phase, which means more signal. All right, so we're going to minimize these T1 differences by waiting a really long time before we come back to slice 1. All right, but we're also going to wait a long enough time that there are these T2 differences between our tissues. We're maximizing our T2, we're minimizing our T1. All right, so let's come back to this graph again. And in this situation, so now it's the reverse, right? Now we want to wait a long TR because we want to minimize our T1 differences. This is our T1 recovery. Remember, we're going back down to B sub 0, and we want to wait a long time. Whereas for our T2 relaxation, our dephasing, we also want to wait a longer time. Remember our other one, we were here at like 5 milliseconds or 10. Now we're here at 70. So that's why I say it's relative to itself, all right? A long TE is around 70 milliseconds, whereas a long TR is like 2,500 milliseconds, okay? So don't compare them to each other, all right? Just try to think of them as separate. But here again, you can see we have really, really good T2 differentiation between these tissues because we waited long enough for the dephasing to occur, all right? Questions on that process? Okay, so let's take a poll. What does TE stand for? Somebody's quick on their typing there. Excellent. Good job, guys. So yes, echo time. And again, that's the time from exciting slice 1 to collecting the echo. It's kind of right there in the name, right? It's the echo, it's the signal, okay? So maybe that can help you to remember it is that, oh, we must have lost somebody and they came back. It's right there in the name, the echo time, okay? So again, let's look at how this actually happens. So here we are, we're starting at B sub 0, everybody's at B sub 0. We flip 90 degrees, it's looking pretty similar, right? But this time what we're talking about is we're talking about a loss of transverse magnetization due to the dephasing. So yes, I've made them different as far as a little bit of T1, but really the biggest difference is that the fat has dephased, so it's shorter, which means it has a less of a component of transverse, which means it has a lower signal, right? Whereas here our water, still spinning together, strong signal from water on a T2 because they're still in phase, all right? And so again, you can see that in the amount of that transverse component of these vectors that's remaining. So here now, our long TR means both tissues fully relaxed to be sub-zero. So this is a T2, we have a long TR, so now we've let them both get all the way back down to be sub-zero, or close, okay? So we're minimizing how much T1 difference there is between them, all right? And we're maximizing the T2 differences. If our TE is too short, we don't have enough dephasing, right? There's not enough difference between these two vectors, right? They're both giving off strong signal because we didn't wait long enough to collect our echo. We're still at that, you know, end of the graph where the lines are too close together. So we don't have good T2 differentiation here because we didn't wait long enough to take our picture, right? All right, so here we have our T2 weighted image. Again, you can see here our TR, long TR, 2200-ish. Long TE, around 80 milliseconds. Again, these are for 1.5 Tesla parameters, okay? Because that's the more common magnet. But again, you can see here we have all of this nice bright CSF fluid, right? Water. And then look how dark this fat is around the periphery of our brain, or our head. And then we've got, obviously got some pathology going on in here as well, but that's, again, it's just fluid that's showing up bright like that. All right, questions on T2? How are we doing at home? Yeah? Good. Great, guys. Okay. All right, so now, which of these is the T2 weighted image? Good, I'm liking the consensus on this one. Excellent, yes. So yes, we can see that there's the bright fluid in the center, the CSF, and then you've got the darker fat around the periphery. So yes, the answer is B. All right, and what imaging parameter controls our T2 weighting? Right off the bat, I love it. Great job, guys. Yes, excellent. So yes, the parameter that controls our T2 weighting is our echo time, or how long we wait before we take our picture. All right, so we've got our T1 down, we've got our T2 down, and then we've got our third type of image weighting, which is our PD, or proton density, okay? The question from the homework, what is PD weighting? So we're gonna go into that now. So how does this all fit together with proton density? First, I want to say, I think there was a question maybe from last week that I wanted to save, that someone asked about the density of the tissue versus what proton density means. So this is just talking about the density of the actual protons, all right? So that doesn't necessarily have anything to do with how dense the actual tissue is on a larger frame, on a larger scale. We're talking on that atomic level scale, okay? So it's just about the density of the protons, not necessarily water versus blood versus, you know, liver, muscle, or bone. It's just the density of the actual protons, okay? So when we talked about T1 weighting, we talked about suppressing T2, correct? And then when we talked about T2, we want to suppress T1, right? With proton density weighting, we want to suppress both, because then what you're left with is properties that are coming from how dense the protons are, okay? So we're actually going to have that long TR, so we're waiting a long time to come back so that our protons relax back down, but we're gonna have a short echo time. We're gonna collect our echo very quickly because we wanna minimize how much T2 there is as well. So we don't want there to be a lot of dephasing that occurs. So we have that short TE. So we take our image very, very quickly. And then what you're left with is the density of the protons that are going to create your contrast. And again, all these three different types of weighting, they're all used to diagnose, obviously, and they all show different things. And in about, I don't know, 3 more weeks, I think, we'll actually get to how each of these is displayed, or how the tissue is displayed for each of these types of sequences. That was a homework question that I'm going to table until that lesson, because I actually will have a pretty detailed sort of a map out of what tissues do what for whatever particular weighting. So at any rate, so we're going to suppress both T1 and T2 properties here. And so here's our situation now. Here we're waiting a long time before we come back to slice 1. So that's our long TR. But we're going to collect our echo really, really fast because we want to minimize our T2 relaxation. And so then again, we're left with proton density. All right. Questions on proton density so far? Well, I'll come back to that, yeah. Okay, so here we've excited. I didn't show the V sub 0, but we all know we started here, right? And then we excited. And then we had some T1 and some T2, but if you collect your signal now, fat and water don't show any T1 or T1, very little T1 or T2 differences, right? They both still have a pretty good transverse component, and they both haven't really relaxed back, right? And so here we have very little T1 or T2 differences. So our long TR means that our tissues go all the way back down, and our short TE means that we don't have a lot of dephasing. And so we have this situation where we're kind of getting signal from both types of tissue, fat and water, but it's based on the density of the protons, as opposed to T1 or T2. All right, so let's look at an image here. And so this is the reason that you'll notice, and you'll start to see it more and more as you sort of get used to seeing these images, that the proton density images are very much grayed out, are they not? They're not as high contrast as your T1s and your T2s because you're getting contributions from all your tissues as opposed to suppressing one or the other. And so that's why you'll start to notice that these look very much more gray than your high contrast T1s and T2s. And that's, again, because you're getting strong signal from both, all right? But again, clinically, this is relevant and useful for other reasons. And so that's one of the reasons that we do it. Okay. So a question from the homework. We're going to talk about our spin echo sequence here. If I understand, using spin and gradient imaging captures images quicker but lesser image quality. Okay, so those are two separate kinds of sequences, okay? So we have spin echo sequences and we have gradient echo sequences. And gradient echo is for next quarter, okay? So be sure that you're looking at your syllabus about what pages you're supposed to read, because you were actually supposed to stop reading right before you got to gradient echo. And so any of the questions that had to do with gradient echoes or gradient rephasing and dephasing, all of that is next quarter, okay? So just kind of put it out of your mind for now, because I want to start with this, which is the most basic kind of sequence. This is your regular spin echo sequence, okay? Another question from the homework. Is the spin echo more desirable because it's maximum signal induced in the coil? Yes, it does have better signal than a gradient echo, and so they are desirable for that reason, but there are, as there always are, there are drawbacks, okay? And so there are reasons why you would run a gradient echo versus a spin echo, one of those being time, okay? But because of the way the gradient echo works, it actually does not have as robust a signal as your spin echo. This is going to be your gold standard. If you had all day to scan and there were no time constraints, this is the gold standard, okay? But for obvious reasons, time being the main one, we have to come up with methods of doing other types of sequences so that we can, be time conscious. Let's see, another question from the homework. Are the densities or signals of water, blood, plasma, all laundry list of tissues generally always distinguishable, or do certain injuries or pathologies make them harder to differentiate? Would any injuries make them behave differently? So the answer in short is no. So whatever the tissue is the tissue, and the properties that make it react how it does to the magnet and to relaxation, those are inherent with that tissue. So yes, you might have a situation where you had, say, a cyst and there was some blood in there and they're intermixed, but again, on that sort of microscopic level, the blood's going to react how the blood reacts. The water's going to react how the water reacts, and that's an intrinsic property that does not change, okay? You might have difficulty diagnosing if there is sort of a mix mash of those, but at the end of the day, the properties of the tissue are inherent to that tissue and they don't change, okay? That's actually, if you look at page 21 and 22 on your book, or in your book, you'll see about the intrinsic properties of your tissues, that they're fixed. And then a question again about where mucus and lymph fluid fall. That is going to be in week 7 that we're actually going to get more specifically into the types of tissues and how they react. Okay, so spin echo sequence. It is probably the most widely used. It's the most basic and it's the easiest to understand as far as the way that it works and how the tissues are reacting, because you basically have, this is it right here. It's a 90-degree pulse, it's a 180-degree pulse, and it's an echo, and that's a spin echo sequence. It doesn't get any more basic than that. The two main parameters, as we've been talking about, are the TR and the TE. Those are the two main ones that you might find yourself needing to play around with or change. The spin echo can generate T1, T2, and proton density weighted images. And because it has that robust signal, it does minimize artifacts. I had one more point about that. And I can't remember what it was. I'll think of it. Okay, so spin echo. All right, so here's a nice little diagram showing us basically laying out what happens when we run a spin echo sequence. Oh, I remember my other point. There was a question, I think, from maybe 2 weeks ago that makes more sense to answer today. And somebody was asking about running a spin echo sequence and is it always a T1? You can basically get most types of weighting with any of the sequences that we'll talk about. There's always pros and cons to using a particular sequence for a particular weighting, but you can get any of those types of weighting with a spin echo sequence. You can get those types of weightings with the gradient echo. You can get them with a fast spin echo. There's all these other types of sequences, and you can get usually most types of weighting with those general sequences. It's just going to depend on the protocols that are at your particular facility. Time is always a factor that you might choose one over the other, but try to think of the sequences and the weighting as two separate things, okay? Is that you can get the weighting with most types of sequences other than the more specific ones like a diffusion or something, but I just want to make sure that you're clear that you can use a spin echo for any of those types of weighting. It's not specific to one. It's just whatever parameters you choose is what's going to determine what type of sequence you get. Is that clear to everybody? Hopefully you're starting to see that in clinic now and it's making more sense. Okay, so here's our spin echo. So we start here, everybody's at 90, everyone's at B sub 0, and we push everybody to 90 with our RF pulse. And then we start to dephase, right? And so here's where we use the 180 pulse to basically flip them so that the fast ones catch back up with the slow ones, all right? And that's called rephasing. That's the 180 rephasing pulse. And you can see here now they're coming back together and we get our echo with them nice and coherent and in phase, stronger signal. You're going to start to see these pulse diagrams. There are several varieties of these, but again, this is just showing you sort of the sequence of events that occur excuse me, in a spin echo sequence. So we've got our 90-degree pulse here, we have our 180, we have our echo. And what do you notice about this distance? It's equidistant, right? The first part is equal to the second part, and that's the 180 happens exactly at half of your TE. And so that's showing you that very, very graphically that it's exactly half. And then this is our echo here. And then these little lines, they're just showing you that this is just one slice, right? We have to do all of our other slices before we come back to this slice, right? So that's just indicating that there was more sequences of this, and then we come back to slice 1 again. And that is our TR, our repetition time, before we get back to our slice number 1. A question from the homework, some clarification on what trailing and leading edge are. Got a bit confused with what it's referring to. Okay, so when the dephasing occurs, right, it's because some of them speed up and some of them slow down, right? And so the fast ones get ahead, that's your leading edge. And then the slow ones get behind, that's your trailing edge, okay? So they kind of fan out like my fingers, but then I flip it and they come back together. And so then when you flip it, the trailing edge becomes the leading edge, and the leading edge becomes the trailing edge, and they all come back together. So that's what the book was talking about with the leading and trailing edge thing. Questions on that? Does that make more sense now, what that was referring to? I can't remember who asked that question, but hopefully it makes more sense now. Okay, and again, here's just another graphic. So we flipped it to 90 there, and this again, here you can sort of see, here's your fast ones, so here's your leading edge here. The fast ones are getting ahead. Your slow ones are your trailing edge, they're getting behind. But when we flip it 180, now our fast ones are gonna catch up with our slow ones. And then here's our rephased echo. Another question from the homework, during spin echo pulse sequence, the second RF pulse of 180 flips the magnetic moments but does not change the NMV from 90 degrees to transverse plane. Okay, I understand what you're asking. Okay, so I think the question is asking that when you flip it 180, does it stay in the transverse plane? And the answer is yes, and you can see that through this graphic. We're still in the transverse plane here, right? We didn't, when I say flip 180, so let's say I'm spinning around like this, right? But I'm gonna freeze right here. 180 degrees from here is here, right? So I'm still in the transverse plane. I'm just flipped from here to here, okay? So hopefully that clears that up. Yes, when you flip it with the 180 degree pulse, at this point, yes, you are still in the transverse plane. Now later we'll learn about another situation where that's not true, but for spin echo, the 180 pulse, you're still in the transverse plane. You're just on the opposite side of it, all right? And again, the fast ones now can catch up with the ones that were slow and got behind, and then they all come together in our lovely spin echo. And that's kind of right there in the name. It's spinning, right? And there's an echo, it's a spin echo. Let's see, another question from the homework. Why does the 180 degree not flip it into the opposite direction on the x-axis? Well, yes, it does. So it would go from, say, here to here, but again, still transverse, all right? Let's see, the 180 pulse rephases. Okay, so yeah, so we're rephasing, so we get the strongest possible signal. And so the effects of our 180 pulse, our 180 rephasing pulse, is that it's going to rephase our dephased protons, and it's going to bring them back together. So it eliminates these two types of signal loss. So our field inhomogeneities, remember we talked about the fact that the magnetic field on that sort of atomic microscopic level, it's not going to be exactly the same in every spot. And we know from our Larmor equation, right, that when our field strength changes, our resonance frequency changes, right? So where the magnet's a little bit stronger, those are the fast ones. Where it's a little bit weaker, those are the slow ones, all right? So the field inhomogeneities cause that dephasing, and then we have our magnetic susceptibility, which again, on that sort of molecular level, the tissues are differently affected by the magnet slightly, and so some are more affected and some are a little bit less, and so again, they're gonna dephase because of that. But our 180 pulse is gonna rephase these two types of signal loss. Really important here is that it does not rephase spin-spin decay, okay? Our pure T2 spin-spin decay is lost forever, and that's what causes us to have contrast, right? If it rephased everything, then we wouldn't have any differences, right? And so it's not going to rephase that T2, which means all of our signal decay is caused by pure spin, and that's what enables us to have contrast between our tissues, okay? So it rephases these two, but it does not rephase the pure T2. Another question from the homework, how is T2 dephasing reduced if the NMV is still in the transverse plane 90 degrees from B sub 0? So, well, I mean, the dephasing is what reduces the signal. And so but again, that's still in the transverse plane, still 90 degrees from B sub 0. So the T2 is just a dephasing that reduces that net magnetic vector, that signal. Let's see, spin goes away permanently. Okay, so spin, echo, weighting. So this is the sort of quick and dirty version. We'll get into some specifics on the next slide. But for our T1, again, we have short TR and short TE. So we're maximizing the T1 differences, we're minimizing the T2 differences. For our T2, again, long, so we're now maximizing our T2 differences and minimizing T1. And then our proton density, we're minimizing both T1 and T2. A short TR and a long TE, that doesn't exist. That's nothing. So that's the only combination of those that doesn't work. And so now I want to address, so from the book, this was another question from the homework. If you guys have your book at home, page 32 and 33, the heat analogy. So this is what this is talking about. So here on the upper left, this is our T1. So we've got our two knobs. We've got our TE and our TR here, right? And so if we're going to turn down our TR and turn up our TE, that's going to turn up our T1. Because we want short TR and short TE, so we're turning them both down to get T1. So that's what this is showing you, that these are pointing to the down. I don't really like this analogy, but somebody asked the question, so I feel like I need to address it. These are both turning TR and TE down, which is turning on our T1. That's what we have here, right? Short is our T1. Then here at the bottom, now we have turned both of them up, which is turning on our T2 weighting. And that's what we have here. Long is T2. And then here, we've now turned up our TR and down our TE. And so we have our proton density. We've turned both of these down, right? We're suppressing T1 and T2. So this is our proton density. So like I said, I don't particularly care for this graphic, but somebody asked the question, so I wanted to try to explain it. I don't remember who it was at home. Did that make more sense what that graphic was talking about, the heat analogy? Yeah? Okay, good. All right, so let's look at some specifics here. And again, we're talking about 1.5 Tesla. So the ranges for these. A short TR is in the range of 3 to 700 milliseconds. Typically, you're not going to want to go over 700 for that, okay? That's kind of the upper limit. You might see some texts push that envelope a little bit, but the higher you go, now you're not going to have as good of T1 contrast, all right, for that short TR. And then short TE would be in the range of 10 to 25 milliseconds. So again, you can see that these are not apples to apples. This is apples to oranges as far as short and long go, okay? But you do need to sort of start paying attention and remembering these parameters for exactly the reason that I mentioned earlier, is if you have to add slices or make other changes to other parameters and it pushes these beyond those limits, you're now not going to be getting the weighting that you really ideally want to get. You're going to be changing the weighting of your images, and you don't want to do that for optimal diagnosis, okay? So you do need to start paying attention to sort of those ranges when you're scanning. I don't know if you've already, perhaps some of you already have seen the text, messing around with them. They will do that, but they do need to stay within these ranges.
I've heard of some of their conversations when, oh man, if we do that, that's no longer going to be a TR or a T1, or now it's clicking.
Good, yeah, see, and you can see why, because if you added too many slices and now you're above the 700 millisecond range, well, yeah, you're now getting away from that T1 weighting that you wanted. So it is sort of important that you at least start noticing that anyway, even if you aren't changing it yourself. At least start noticing what those parameters are on your sequences. So here we have our long TR, 2,000 plus milliseconds. And then for our long TE is anything above 60. And so again, you can see there's a very broad range in these two different parameters, because TE happens T2 happens a lot faster than T1 relaxation. Okay, that dephasing happens very, very quickly. Question from the homework: what is the difference between long TR and short TE? So here's your differences right here. These are your parameters that you're gonna want to start remembering. And again, don't worry about the gradient echo portion of the chapter. That's next quarter. All right, so let's take a poll. So which of the following would produce a T1 weighted conventional spin echo sequence or image? And what I recommend you do for these is evaluate each of those two parameters and look at your ranges and say, okay, is this short or is this long? And for each of the two. And that way you can determine which of those would produce that. And this is a type of question that you will definitely see on boards. And in fact, you'll probably actually see it. They'll give you a picture and they'll say, which of these parameters created this image? And so you're not only going to have to know your ranges, but you're going to have to be able to first even identify what type of image that is. Is it a T1 or T2 or proton density, okay? So that's why it's really important that you sort of get this stuff down. Great. Yes, yes, yes. The answer is A. So we have our short 500, that's below 700, right? So that's a short TR. And then our 30 millisecond TE, that's still considered short because it's still under 60, okay? So yes, the answer for that one was A. So now, how does a short T1 tissue appear on a T1 weighted image? And so again, take the question apart. If it sounds confusing in your head, think, okay, well, first of all, which is my short T1 tissue? Okay, well, figure that part out. And then, well, okay, how does that look on a T1 weighted image? We're getting better consensus there. Yes, so first, what's our short T1 tissue?
Fat.
It's fat, yes. And so we know now we're talking about fat, and we're talking about T1 weighted. So how does fat appear on a T1? It appears light, right? We all agree on that? Okay, so another one. Now let's talk about T2 weighted. Which one of these created our T2 weighted image? And again, take the question apart. Think in your head, okay, what do I need for T2, for TR and TE? Long, short, which one? Oh, we're split. Okay, yeah, we're getting it. Yes, so what do we need for T2? We need a long or short TR? Which one? Long. And what about our TE, long or short? Long. So we want long, right? Yes, the answer is E. So that 2200, that's a long TR. That's above 2000, right? And then 90 for our TE, that's above 60. So that's also considered a long TE. So yes, the answer for that one would be E, 2290. All right, last poll of the day. Which of these would have produced the PD weighted? So again, ask yourself which one I need long and which one I need short or long, and then figure out from there. We're all over the map here. All right, so the correct answer is actually D, which more of you got than, well, now half of you. But so again, ask yourself for a proton density, what do I need for my TR? I need a long TR, right? But for my TE, I need that to be short. And so when you evaluate those parameters, D is the only one that matches that description. C is not, 1,000 is not long enough for long TR, right? It has to be above 2,000. So that can't be it. And then for E, the TE is way too long. We need a short TE, and that's 90 is away, that's a long TE. And so the only one that could possibly create your proton density is going to be D, all right? So questions on any of that? How about at home? Are we good? How are we doing? Getting some thumbs up. Great. Okay, so let's review our objectives that we named at the beginning. So we named the parameter that controls our T1, and we now know that's TR. And we know that TR stands for repetition time. We also know that that means the time between exciting slice 1 and then going through all of our other slices and coming back to slice 1. That's our repetition time. We also now know that TE controls our T2 weighting and that TE is our echo time. So that's the time from when we excite our tissues to when we collect our echo or our signal, and we could also call it. We can now describe a proton density weighting and how the TR and the TE affect it. So we know that we want that long TR, right? So our tissues relax back down to be 0. And we want that really short TE so that there's not a whole lot of dephasing going on. We want to suppress T1 and T2 characteristics. And what we're left with is simply our proton density, the density of the actual protons in your tissues. And then we can describe our basic events in a spin echo sequence, and that's, what is it? It's 90, 180 echo, right? It's just as simple as it can possibly get, 90, 180 echo. And then we can identify our relative lengths of our parameters for the T1, T2, or proton density weighted. And again, that's something that you definitely need to look at those limits, okay? Start paying attention in clinic so that you can make those correlations, okay? I did have one more thing that I neglected to answer a couple of the homework questions at the beginning. So I wanted to address that now. Let me get out of this. Okay, so a question from the homework, a gradient echo pulse, let's table that till next quarter. The heat analogy, I did get to that. So what is meant by magnetic isocenter? All that means is the exact center of the magnet, which is where the magnet is most homogeneous, okay? It's gonna be, if you're in a 1.5, the center of the magnet is always gonna be 1.5 Tesla. Okay, if you're 3 Tesla, the center is always gonna be 3 Tesla, okay? So that all it means, magnetic isocenter is just the exact dead center of the magnet, and as you go in either direction, any direction, away from that, you get less and less homogeneous, okay? And then what function does it provide? So the function, I wouldn't say it's really functional, but it just so happens that when we talk about gradients next week, that the center actually serves as a fulcrum. It's like a seesaw, okay? So the center is the center of the seesaw. It's the fulcrum because it doesn't change. The rest of the magnet we're going to find out is actually going to change, but our center, our isocenter, is always going to stay the same, and it's that seesaw fulcrum. But we'll talk about that next week. I just kind of wanted to address those last couple of questions from the homework. Don't forget to do your homework. I think there have been a couple of people that didn't turn something in, and it's for points, but it's really more to help you as you're reading through. If you have questions, that way I can add them to the lecture and address them, to the whole class so that the questions get answered. I just don't want you guys to be left with questions that aren't being answered. So other than that, I know we're a short lecture today, but any questions? Concerns? Please look. Oh, let's see. Can I turn this up? Let me turn up my volume. Hang on. Okay, try again.
This is Eric. I have a question.
Yes.
And as far as the math goes, is there some examples we can go off to do the math homework?
It shouldn't be due next week. It should be due the next week after that. Because we're going to do the math next week. We're actually going to do math in class next week, Eric. So we'll be practicing that next week, and then hopefully, because it's not easy math, and so I don't necessarily want you to attempt to do it. However, that being said, there is a math practice quiz. It says math practice quiz that you can take up to, I think, 10 times, and every time you take it, it'll generate random numbers. So they're not going to be accurate, that like you wouldn't have a 1.36 Tesla magnet, but it's just in order for you to practice the math. Right now, the only math that we've been over so far is the Larmor equation, and so I don't want you to get too far ahead of trying to figure out the math that we'll do next week, because it's, like I said, it's not exactly easy math, but once we do it in class together, then hopefully it'll make more sense. Is that an acceptable answer?
I think he was just asking because, like, under the modules, it was under.
Oh, it's under
week 3. Yeah.
Oh, okay. I think I put it there so it would open the practice quiz. Is that what you're talking about? Yeah, I just put it there so it would go ahead and be open. But we'll actually be covering the majority of that math next week, and then it'll hopefully make more sense then. Other questions? I'm glad to hear you, Eric. You got a microphone. All right, guys. Well, if you again, as always, if you think of anything, please don't hesitate to email me. And also, again, be sure you're looking at the PDF of that syllabus, because that's where you're going to see your assignments, what's due, what page numbers you're supposed to read, what page numbers you're not supposed to read, so that you will be in sync with us. All right. Well, thank you, everybody. Yeah.
Flu shots?
Flu shots. I emailed you.